Alright, in this video I'm going to talk about the fundamental theorem for line integrals. So if you remember from first year calculus, the fundamental theorem of calculus is something like this, where f of x is the derivative of this other function. Okay? Well, with line integrals there's an analogous fundamental theorem. And I will just skip right to it and show you what it is. Right, let's say that I have some function f, and it's a function of x, y, and z. If I find the gradient of this function, okay, the x, y, and z components are all going to be functions of x and y, because f is a function of x and y. So this is going to be this gradient, the gradient of f is going to be a vector field. So then, the fundamental theorem for line integrals states that when I take the line integral of this vector field and I dot it over some path, then what I get is the value of my original function, evaluate it at one end. So I'm just going to write that like I'm just going to write it like this. Okay, maybe where t equals a, t equals b, and r is a function of t. Okay, so maybe at first it might seem a bit strange, but if you think about the if you think of the fundamental theorem of calculus, the thing that's inside the the integrand here is a derivative of this other function f, right? Well, the gradient of f, you can think of that sort of in a similar way, where the gradient of f is sort of like a type of derivative of this function f. Okay? So I'm going to show an example of this. Okay, so I first want to note that not all vector fields are gradients of some other function. Okay, if you have a function, if you have a vector field that's something like this, where everywhere in the plane our vectors sort of like circulate like this. I mean, what would it mean for this guy right here to be a gradient of some other function? Well, f would have to be some function of x and y. F sub x would have to be y, and f sub y would have to be negative x, right? So that way the gradient of this function would equal f, like what I wrote here. Well, what do we know about partial derivatives? There's a theorem where if you take the derivative of a function with respect to x, and then you take the derivative of the function with respect to y, that's going to be the same thing as if you were to first take the derivative of a function with respect to y, and then take the derivative of the function with respect to x. So you can see here that this is f sub x and this is f sub y. Okay, that's what we have here. So if we were to take, using these components of this vector field here, if we were to take the derivative of the x component with respect to y, we would get 1, and then if we were to take the derivative of the y component with respect to x, we would have negative 1. And you can see that these two guys do not equal, which means that there is no function that has the gradient of this guy right here. Okay, and since these two don't equal, this means that f is not a gradient field. Another way to think about it, I can make this claim. Okay, so f is the gradient of some other big F. Vector field big F is the gradient of some other function little f if the vector field big F is conservative or path independent, which means that if I were to start at some point in the plane and then finish, let's say, at some other point in the plane, and then I were to travel from, let's say this is just point 1, let's say this is point 2, let's say I were to travel from point 1 to point 2, like this. Does my path matter? Well, if f is a conservative vector field, then no, the path doesn't matter. So you can think of this like, the work that you have to do to lift a big huge rock up a hill, right? If you were to start at the bottom of the hill and you were to carry that rock all the way up to the top of the hill, well, from like high school physics, the work would just be where this is your height here. So the path that you took from the bottom to the top of the hill didn't matter. You could have went upstairs, you could have went up a steep hill. So in this example, the work is path independent. So back up to this example, you can see that if I were to choose, let's say, a path that sort of followed these arrows around like this, if I wanted to calculate the work that this vector field performed on a particle moving from P1 to P2 along this particular curve, let's call that C1, you would see that all of these, let's just call them force vectors, are sort of pushing me in the same direction. So I am, and since I'm displacing in the same direction as the force, then if I were to travel from P1 to P2 along curve 1, then in this example my work would be, the work that the vector field performs on me would be positive. But hopefully you can see that if I were to choose this path, let's call that C2, then I would be going against these force vectors, which means that if I were to travel from P1 to P2 along this curve, then the work would be, the work that the vector field performs on me would be less than 0. So this tells us that this example here is not conservative, which means that this vector field big F is not the gradient field of some other function. Okay, so this example that I'm going to do relates to the example that I just talked about carrying a rock up a hill. You might remember from physics that the magnitude of the force of gravity is equal to, say, like your mass times the mass of the Earth times gravitational constant divided by the square of the distance from like the center of the Earth, right? Well, if we were to extend this concept into three-dimensional space, then r would be the distance from the origin to some point. Okay, so that would be the distance formula, the square root of x squared plus y squared plus z squared. And this is just the magnitude of the force. So if we wanted the actual direction, the direction would be, the direction would be in the direction of some unit vector that points from the point that you're at to the origin, where the unit vector would literally just be the position vector to where you are divided by the length. Okay? So if we were to plug all this stuff in, then we would have a vector field, the equation of a vector field. Well, first let me say that this vector field is going to be the magnitude of f times that unit hat vector. Okay, so here's the magnitude, there's the direction. So then when I plug all that stuff into this guy right here, I get this vector field. Okay, so I don't want to go through all the algebra of how I got this, because I have a feeling this video is going to be longer than what I was hoping. But hopefully you take my word for it that this is going to be the vector field of gravity. Okay, so just to simplify things, if I were to let the product m, little m, big M times g be equal to 1, just to simplify all my calculations that I'm about to do, and then I were to plot this vector field, I would have something that looks like this. Okay, so I made this little sphere here and colored it blue and green to represent the Earth, and then all of the arrows that you see around this little sphere here are from the equation that we just found. Okay, so just to show you, here are all my equations here. You can see I have each of the components here, and for little m times big M times g, I just have 1. If I wanted to know the work done by this vector field on a particle that moves from some point up here down to some point close to the Earth here, how would I do that? Well, I can do it one of two ways. I can use the Fundamental Theorem, which we'll do quickly, and then we'll compare that to the actual calculations that we get from calculating the line integral. So just to show you what I mean. Okay, so here's a little animation. Well, I'll start it in a sec here, but what you see here are the scalar equations of a parametric equation for a position vector that traces out a line actually that goes from this point here, which I'll tell you what that point is in a minute, down to this final point here. So this animation is going to actually show that position vector trace out this line here. Okay, as t goes from, well, we'll find out from 0 to 1. Okay, so that's pretty neat. So we'll find the parametric equation for that line here in a minute, and then we'll have a look at the line integral. Okay, so in this question, point 1 is going to be the point 3, 4, 12, and then point 2 is going to be the point 2, 2, 0. So we're going to go from point 1 to point 2. And since I didn't specify the path, we're going to choose to go directly from point 1 to point 2, so a line from point 1 to point 2. Okay, so it's going to be some position vector, some initial point. Okay, so let's say that we start at the point 3, 4, 12, and then we want to parameterize it in terms of t, and then we want a vector here that goes from point 1 to point 2. Okay, so that would be like the directional vector. So point 1, point 2 would just be, you know, P2 take away point 1 here. And then since R is F, Y, Z, then our scalar equations are x equals 3 minus t. So you can see up here that when t is 0, we're at the point x equals 3, y equals 4, z equals 12. And then when t equals 1, we're at the point 3 minus 1 is 2, 4 minus 2 is 2, and 12 minus 12 is 0, which is P2, which is I erased, but that was P2. So we know that we're interested in this position vector when t goes from 0 to 1. Okay, so that's going to be our line integral. Okay. So I said that gravity was a conservative force, or that this vector field F was conservative or path independent. So how do we find the function f that f is the gradient of? So how do we find f? Well, there's a couple different ways. I'm not going to go into how to find it. It's not very hard, but basically I'm just going to tell you what the final answer looks like. Okay, so if you were to take the gradient of this function, then what would you have? Well, fx would be minus 1/2 mmg over all this stuff, 3/2, times the derivative inside. Okay, so this is the chain rule here. So you see that these 2's would cancel there, and you would just have 3/2, which is the x component for f, which is, you can see here that the x component of f is negative x over this. Okay, so it would be similar for y and z. It would just be y over this and z over this. So I'm not going to bother going through to show you f sub y and f sub z, but hopefully you take my word for it that this little f right here is what they call the potential function. Okay, so since we said that the gradient of little f is big F, then we can rewrite this. So line integral over the curve C, which was this line that we parameterized, is going to be the gradient of f dotted with dr, and then from the fundamental theorem for line integrals, it's going to be the value of f evaluated at our two endpoints. Okay, so of course, to evaluate these guys here, you're going to have to plug in what x, y, and z equals in all these spots right here. So let's just quickly go ahead and do that. So remember I said that this product here of these three guys, I'm just going to let equal 1, just to simplify things for me. So I'm going to go ahead and make these substitutions. Okay, so I plugged in all my values here. I'll go ahead and perform all the algebra. 1 over the square root of 169. So that's the same thing as 1 over 2 root 2 minus 1 over 13. Okay, so here's our answer here. Now let's go ahead and see if we can find the same thing by calculating the line integral. Okay, so let's figure out what dr is going to be. Okay, so if r is this guy here, well, dr is going to be r prime dt. So r prime is going to be, well, the derivative of the x component. It's going to be a vector. The derivative of the x component is -1. The derivative of the y component is -2. So let's go ahead and do this dot product. Okay, so when I go and perform that dot product, I take the x component of this guy here, so it's negative x over this, and then I dot it with the x component here, so that's -1. So the negative signs cancel, and I just for this term here, I just end up with x over this denominator. And similarly, the same thing happens. The negative signs cancel. For the y term here, I have 2 times y over this. And for the z term, I have 12 times z over this. So now I'm going to be integrating this with respect to t as t goes from 0 to 1, which means I'm going to have to make all my substitution for x, y, and z in terms of t here. So this gets kind of messy, but for x, when you sub in 3 minus t, for y, when you sub in 4 minus 2t, and for z, when you sub in 12 minus 12t, they're all over the. Why did I write it like this? They're all over the same common denominator. So when you put them all over the common denominator, you end up getting this. Okay, so for this denominator here, I actually subbed in x, y, and t, expanded them out, combined everything all together, simplified it as much as I could, and this is what I got for my denominator. I can simplify the top, and I end up with this. So you can see here that if I let u equal 149 t squared minus 310 t plus 169, then du is going to be dt. And then if I factor out a minus 2 out of this, I get 149t. These terms right here are found right here. Okay, so I I can substitute this stuff in. I can substitute in place of these guys here, I can substitute negative du over 2 to simplify this integral. And it simplifies quite nicely. My integral simplifies to this when I make this u substitution. So when I integrate this, I get, okay, so when I evaluate this at the two ends, you can see that these two guys cancel out, and I have 1 over root 8, take away 1 over root 169, which we said equals that guy right there. You can simplify this to turn it into that. Okay, so you can see that given our initial problem, there was two ways to solve this. One using the fundamental theorem of line integrals, which I erased. I don't know why I keep erasing things. I can keep making new pages. Or you can do it the hard way. Well, it wasn't really hard, it was just sort of long and tedious. I skipped some of the algebra here. But you can see that using the fundamental theorem of line integrals simplified things a lot. The only problem was making sure that this vector field was conservative. And like I said, let's say that f is a function m, and let's say that x is a vector field with m and n. Well, to test whether or not it's conservative, you take the y derivative of the x component and take the x derivative of the y component, and you look to see if they're equal. And if they are equal, then f is a conservative vector field, and then you can apply the fundamental theorem of line integrals.